type of chemical equilibrium exists between substances that are soluble or partially soluble. So what do we mean by solubility? Well, if something is slightly soluble, that means when it's placed into solution, it goes through hydration, and the water molecules pull the anions and cations apart. If it is slightly soluble, like this mercury bromide, all halides are soluble except for mercury, silver, and lead. So this is slightly soluble. That means that as the water pulls some of these anions and cations apart, those cations and anions are attracting to one another and going back to being a solid. This means that this salt, mercury 2 bromide, is slightly soluble. So how do you distinguish what is soluble and slightly soluble? The fine print of what we define as soluble is that you can dissolve more than 3 grams of it in 100 grams of water. So what happens if you can only dissolve 2.9 grams? You are slightly soluble. So the word soluble is not an absolute term. And same with insoluble. Things that are insoluble, you can have varying degrees of insolubility. And slightly soluble or insoluble, I'm doing air quotes, you can't see them, solids, initially you have no concentration of the ions in solution. However, if you add some of the solid, those ions will eventually dissociate, go through hydration, and you'll have some concentration. Let's add some more, make it a nice pretty example. Once hydration occurs, the solution is termed to be at equilibrium and is said to be saturated. When the rate of ions colliding to form solid equals the rate at which the solid is undergoing hydration to form ions. And since we're at equilibrium, we can write an equilibrium constant for this reaction. So for this, I have silver bromide dissolving into water. So to write the equation for that, it would be silver bromide becoming silver and bromine ions, or bromide ions. If I asked you to write the equilibrium expression, or the equilibrium constant for this, you would write the concentration of silver ions times the concentration of bromide ions. And we would leave out silver bromide because it is a solid, and its concentration would be so astronomically high that it would totally offset our calculation. So we're going to completely ignore it. It's negligible. The change in its concentration is so negligible it won't matter. When you're dealing with solution equilibrium, we're dealing with slightly soluble or insoluble substances. K is given a special subset. It's called KSP. It is your solubility equilibrium, or solubility product, because it is the product of your concentration of ions times your concentration of ions. It's your special K, and it's experimentally determined. So the value of KSP, the value of your solubility equilibrium constant, can change depending on where you get your information from. So in your notes, there's a table that looks like this, that gives us a KSP value for common ionic salts. You'll notice that these can get astronomically low. Like over here you can see times 10 to the negative 54th, or one we're going to use later that I've already Googled is bismuth sulfide. So I'll go ahead and add that. That one's astronomically low as well, 1.8 times 10 to the negative 99th, which means that if I have a mole of this, 1 point and 100 zeros with a 1 after it, that's how many moles of one bismuth ion I would get from this when it dissolves. So these are all usually astronomically low when you have something that's known to be insoluble, or at least by the air quote definition of insoluble, because while it is insoluble, you will get some ions. So if I'm giving you a table and I ask you to tell me what the KSP is of silver bromide, well, you can just look at your table, Silver bromide is a bromide. We're looking at silver, so it's 5 times 10 to the negative 13. And that's all well and good if you're in general chemistry. But this is AP, so we know it's not going to be simply that straightforward as, hey, look at the table and tell me what you want. It may be for part A of a question, but it definitely is not going to stay that simple. So let's move on to something a little more complicated. Now this is more like an AP style question. Determine KSB and determine molar solubility and concentration of each ion. Well, concentration of each ion, I expect you kind of know what concentration is by now. KSB I just explained, but what on earth do I mean by molar solubility? Molar solubility goes by a couple different terms. You can call it molar solubility, you can call it the solubility, or you can call it the molar solubility of the solid. And all of those things boil down to, and this is what you are going to think in your head from here on out, anytime you see molar solubility, or molar solubility of the solid, you are going to think X. Find X. X? What X? L, you're just throwing letters at us. I am not. Remember back to your rice table when we're not calling it just rice, we're calling it rice-E, because there's a rice, when you get to equilibrium, we express it in terms of X. You're going to find what that X is. So, but before we can do anything, let's write these solids, or semi-soluble solids, as equilibrium expressions. So silver sulfate breaks down into 2 silver ions and 2 sulfate ions. Notice I've written it into my little rice table here. So initially, I have a lot of this stuff, and the concentration is so large that this entire column here underneath of the solid I'm going to outright ignore. I'm just going to put a big X through it because I have no use for that entire column. Do not judge my scribbling. I only have a mouse pad. Alright, initially I have no silver ions or sulfate ions in solution. But as this reaction occurs, as silver sulfate goes through this reaction, I end up increasing. How much do I increase their concentrations by? Well, I have to pay attention to the stoichiometry. This is going to increase by X, but by 2X, because there's 2 silver nitrates. And there's 1 sulfate, so I'll increase that by 1X. Therefore, at equilibrium, I would have 2X and X. And I've skipped ahead in all my excitement to tell you what X and molar solubility is. I totally forgot. First part of this was very cut and dry and simple. Determine the KSB. So I go back to my table. I'm looking for silver sulfate, which was hidden by my menu. Here it is. It's 1.2 times 10 to the negative 5. So that would be 1 point. Okay, back to my original ramblings. Now that I've expressed this in terms of X, if I know that this is what KSP equals, and I know that KSP equals the product of our concentration of silver times our concentration of sulfate, and I pay attention to the stoichiometry and know that I have to square the silver, because it has a coefficient of 2, this would be my equilibrium expression. Please, 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 for the love of your score and our collective bonus at the end of the year, do not skip the step of writing your equilibrium expression on any equilibrium problem, even if it doesn't ask for it, because oftentimes they might not ask for it, but they will give you points if you place it. So this is my equilibrium expression. Notice it was not asked for, but I'm going to put it on here because I want those free points. Okay, so I know that this is the equilibrium expression. I know this in terms of X, and I know what it equals. So this whole thing equals 1.2 times 10 to the negative 5th. I can express that in terms of X. So where I have silver ions, I'll plug in 2X. Where I have sulfate ions, I'll just plug in X. And now I have a very simple math problem. 1.2 times 10 to the negative 5th equals 2X squared. So 2X squared, don't you dare pull out that calculator, that's just easy thinking. Alright, 2 squared is 4, X squared is X squared. Times X, It's not going to be x squared anymore. It's going to go to x cubed. Alright, divide by 4 on both sides. I end up with 3 times 10 to the negative 6. If I take the cube root of that, so I can do that one of two ways. On my calculator, I can hit math, and the fourth option down is the cube root, or I can take that value and raise it to the 1 divided by 3. Either way, you find that x equals 0.0144. 2 sig figs, 2 sig figs. I was given 2 sig figs in my problem, so let's call that 0.14. And this is not a naked unit. While K is naked, has no units, this is a what? This is a concentration. So I can either put that in brackets, meaning it's a molar concentration, or I can put molarity after it, or I can put moles per liter. Alright, now that's the second part of this problem. The third part is to determine the concentrations of each ions at equilibrium. So now we're just going to plug this in, plug x in here, and 2 times x, we come out with 0.029 molar, and for sulfate we end up with 0.014 molar. Alright, see if you can do the next one. Pause me and see if you can do the next one. To save some time, I'm going to put up all the work at once, and I'll give you all the answers at once so you can check yourself. Alright, chances are you've probably pulled your hair out 3 times because your calculator kept saying x equals 0. And for the most part, x does equal 0 because you've taken your calculator beyond the limits that even it can go. So, what does this mean? That means that such a small, infinitesimally small number of bismuth ions break away and sulfide ions break away, that there is absolutely no concentration, no discernible concentration that your calculator, at least in its current form, can calculate. So this would be a perfectly fine example. So to say that 0 molar and 0 molar, this would be almost completely, and by almost completely I mean the fact of this class, is completely insoluble because its KSP is so massively small. Can you say that? Massively small. Alright, let's go the opposite direction. Calculate KSP for, crap, it's that guy we just did. But this one we'll actually be able to get an answer for, I promise. For bismuth sulfide, which has a molar solubility of 1.0 times 10 to the negative 15th moles per liter at 25 degrees Celsius. Quick note to draw your attention to: all values, all KSP values, are temperature dependent. Some things are more soluble at higher temperatures. That's not always true, but most things are more soluble at higher temperatures, less soluble at lower temperatures. So anytime you're given a temperature, it's important to note that, and you might be asked, why is something more or less soluble at a given time? Look at the difference in temperature, because a difference in temperature is going to give you a different solubility. Okay, so calculate KSP for bismuth sulfide. Molar solubility is 1.5 times 10 to the negative 15th. Well, what is that molar solubility? Paying attention, you that know that molar solubility is code for x equals. So now this simply becomes child's play. Let's write the equation again for this, and I've just looked at the time, so I've taken the liberty of filling out most of the rice table so that the next part goes rather quickly. We know that KSB for this one equals the concentration of bismuth times the concentration of bismuth cubed times the squared times the concentration of sulfide cubed. And again, for the love of gosh, please write that. Alright, we can express this in terms of x. So let's plug in x for these. And we can combine all of that into one large equation. And now comes the easy part. Simply plug in x. So this becomes 108 times 1 times 10 to the negative 15th to the 5th. We plug all that into our calculator, and this time we actually do get an answer, and we come out with 1.1 1 times 10 to the negative 73rd, which is the correct answer, but it's different than the value we have on our table. Why? Why is it different? Because remember, KSBs are experimentally determined values, and therefore they can alter based on the experiment, can alter based on any number of variables, but they can change. So this is the KSB for this particular problem. So there are a couple summations I want you to get from this. First off, molar solubility always is code for X. Anytime you see it, please cross it out and write X so that you know I'm looking for what is X in my Rice table. Please notice that there is never a coefficient. Never, ever, ever. This is one of the very few cases in science where you can say never. There is never a coefficient on the solid. You will never put a coefficient on the solid. If you need to put a coefficient on the solid, you messed up in your dissociation. You will always respect the stoichiometry of the reaction. So whatever coefficients, you have to apply them both to X as well as to the exponents. It is possible to compare the solubilities of two things given their SPs, but you need to be extremely careful because these comparisons can only be made for salts that have the same ion to ion ratio. So something we can compare bismuth sulfide to something else that has a 2 to 3 ratio of cation to anion. Don't forget that solubility can change with temperature. Some substances are less soluble in cold, but are less soluble in hot and will become more soluble in cold, and vice versa. It's an unknown. You need to know that information if you're going to make that justification on an essay or free response.